All right, today we are doing 1.3a. We're doing evaluating limits analytically. So last section we learned about how the limit does not necessarily depend on the value of f of x at c. However, sometimes, let's say we have a line and we're looking for the limit at 2. At this point 2, our limit here is going to be this point on this line. Because from the left and the right, it's approaching the same, and it just so happens that it is precisely the point f of c. It is precisely that point on the line. So in such cases, the limit can be evaluated by direct substitution. So all that that's saying is if we plug x into the equation, we get the point there, if it is something to where the limit actually lines up. So some basic limits here. So if b and c are any real numbers and n is a positive integer, the limit as x approaches c of b equals b. So this means if we have some function b, it's not changing because there's nothing there to plug in for x. So it's just b. It's like if we said, okay, we have the line y equals 3. What's the limit as x approaches 5 of y equals 3? It's still 3. Okay, the limit as x approaches c of x is c. If we have that line y equals x, if we plug in 2, we get 2. Whatever we're plugging in for x replaces it because it's just the line y equals x in this case. The limit as x goes to c of x to the power of n is c to the power of n. So same thing, that base is x, we just plug it in, and it's just changing it. So if we had x to the power of n, so if it was 3, we would plug it in, it'd be 3 to the power of n. It would give you that function. So you're just substituting it in because that's all that's changing it. So let's look at example 1. The limit as x goes to 2 of 3 equals 3 because there's nothing to plug in there. The limit as x goes to negative 4, we substitute it directly in for x because it's just x. Limit of x squared, plug in 2. 2 squared is 4 because it's just substituting it in for x there because there's nothing crazy going on, no holes, no jumps, no piecewise, so we're good. So we have some different properties here. This is just saying that the limit as x goes to c of this function is L, so whatever limit we get. And the limit of g of x is k. So it's saying that if we have some number that we're multiplying on the outside of our function, like 3x squared, the limit of x squared, we would just multiply it by that 3, or whatever's out front. If we're adding two functions together, we can add their limits together. If we're subtracting two functions together, we can subtract their limits together. If we're multiplying two limits together, we can multiply their limits together. If we multiply the functions together. If we're dividing the functions, we can divide their limits as long as that denominator isn't 0. And if we take the limit of something to the power of something, we can just do the same thing with that limit there going forward. So that's just some kind of properties there that can help us out. So we're going to look at some more basic limits. This one's a limit of a polynomial. This is going to be a function that does not have any holes. We know it's going to be a quadratic, no piecewise, nothing. So in this case, we know that we can just plug it straight in. We can do direct substitution. And yeah, so we're just going to plug it right in. 4 times 2 squared plus 3. We could even split this up if we wanted to. So this is how we know that we can do direct substitution. The reason being that we can split it into two limits. The limit as x goes to 2 of 4x squared plus the limit as x goes to 2 of 3. This is getting a little proofy here for you to see why we're doing it. And then this one, we could pull that out front. And then the limit as x goes to 2 of 4x squared. These are the two properties we learned. We multiply it by 4, we square it, plus the limit as x goes to 2 of 3. So we plug in 2. 2 squared is 4. 4 times 4 is 16. Plus the limit as x goes to 2 of 3 is just 3, since it's just flat, and that would be 19. This is the same thing as just plugging it straight in. So with that, we know that if we have a polynomial, this is valid for all polynomial and rational functions. And so that tells us that we can just do direct substitution there. And then we can also divide as long as the denominator is not 0. So let's look at this guy. Example number 3. Find the limit of this function here. What happens when we plug in 1 to the denominator? Would we get 0? No, we wouldn't. So we can actually just plug it in directly. If it gave us 0, we couldn't do direct substitution. There would be other ways to solve for this limit. But since we do not, we can plug it in directly. 1 squared plus 1 is 2, plus 2 is 4. 1 plus 1 is 2, and we get 2. Yay, so now we're just doing like easy algebra. It like looks so crazy, but we're just plugging numbers in, guys. Try to be doing some of these without calculators too, because these would be questions on your AP test that wouldn't have a calculator. Okay, composite function. The limit as x goes to 0 of x squared plus 4. So we know the limit as x goes to 0 of x squared plus 4. We could plug that in. We proved that already up here at the top with our polynomial function. So that would be of x squared plus 4. We plug in 0. 0 squared plus 4 is just 4. And then what else we know, if we split this into two pieces, the limit of x, the square root of x, I'm splitting this into a composite function, like x squared plus 4 we could substitute in there. But the square root of x going to 4, would be, as we're plugging in this here, the limit as x goes to 4 would be 2, because I'm plugging that in for my composite function. So this is just proving that if I have that square root, I can plug it straight in. 2 squared plus 4 is 4 plus 4, which is 16. Hold on, guys. Sorry, I plugged in 2. I should be plugging in 0. I'm showing you can plug that in. Sorry. 0 squared plus 4 is 4. The square root of 4 is 2. So there, it works the same way. So like with knowing that, we can do the same thing here. This is a composite function, and so we could plug it straight in. The third root of 2 times 3 squared minus 10. 2 times 3 squared is 9 times 2, which is 18, minus 10. The third root of 8 is 2. And so that works too. We could have split it up into like the two functions. My pen is dying. Sorry, guys. So the limit as x goes to, like we could have split it as x goes to 3 of 2x squared minus 10. That would give us 8, and then we would plug it in the limit as x goes to 8 of the third root of x. But that's just showing us that we could plug it in as a composite function and still get the same thing as direct substitution. You wouldn't have to do both ways on your homework. Cool. Let's do some trig functions. Woo, woo. So these we learned that there is a theorem that says that for any of our trig functions, as long as c is a real number in the domain, we can do direct substitution for any of them. So like for the limit as x goes to 0 of tangent of x, I can just plug that straight in. Tangent of 0 equals 0. So you're going to need to remember your unit circle. Right here, we would have 1, 0. So tangent would be sine over cosine, which is 0. Limit as x goes to pi. This we could split up into the two things and then multiply them. The limit of x going to pi would just be pi. Limit of cosine pi. So remember, pi is over here. -1. So we have that -1 times pi is negative pi. Then the limit as x goes to 0 of sine squared. So sine here would be 0. And then we square that, which gives us 0. So that's kind of the introduction there to your 1.3 evaluating limits analytically. Thank you.